Okay, hold on 1 minute. Let me check something here. To make sure. Okay. I think I'm live. Where is, okay. I just want to make sure that I'm live, but I don't see.
I think you are live because it says on my computer screen that you are.
Okay, all right. I'll take your word for it. All right, okay. So as I recall, the last time we were here, we were discussing the nomenclature of, let me see here. I know the next thing we're supposed to discuss is naming acids. We talked about binary ionic compounds. We talked about naming compounds with polyatomic ions. We talk about using the stock system and the classical system for naming ionic compounds where the cation can display more than one charge. So scroll down. Okay, and I think we discussed, and somebody can correct me if I'm wrong, we discussed naming binary molecular compounds like this one, right? This one here, right? Did we? Can somebody tell me?
Yeah, we discussed it.
Okay, so let me scroll down. Yeah, I think I remember discussing this. Okay, so, okay, let me hurry up and scroll down too. Okay, right. Okay, so now we're going to talk about how do we name acids that are derived from binary compounds. So there are certain binary compounds which contain hydrogen. And as such, when they're dissolved in water, they form acid solutions, all right? Okay, what's going on here? Daggone it. Okay, so basically what you'll find is that the solutions of these compounds are given names that indicate that they're acids. However, the original compound that would be dissolved in water would not have the same name as they do. In fact, their names end with IDE, like any typical binary molecular compound. Now, in these compounds, hydrogen is typically the first element in the formula, right? So basically, we're talking about binary compounds which contain hydrogen. So you have hydrogen basically combined with some other non-metallic element. And that compound, when dissolved in water, will produce an acidic solution. So basically, what you're going to start off with is your binary hydrogen compound, which in and of itself is not an acid, but when it is added to water, as shown in this diagram here, then the resulting solution will be an acidic solution, right? So that's what we're talking about here. So a couple of things we need to talk about in terms of the naming of these compounds. If you're talking about a pure compound, it is named as a binary molecular compound. Now, there's one particular important difference between naming these compounds and other ordinary binary molecular compounds, and that is that no prefixes are used. So, for example, in the case of, hold on, I can't write on this. In the case of this compound here, by itself, before you add it to water, this is called hydrogen chloride. I was hoping that I'd be able to write on the screen here, but apparently, let me see here. Oh, okay, pen. All right, so the name of this compound, before adding it to water, this is called hydrogen chloride, all right? So you'll notice in this naming of this compound, there's no prefixes used, no prefixes, all right? And that's typically what we do when we're naming these binary molecular compounds where one of the two elements would be hydrogen, right? We do not use any prefixes. We simply say hydrogen, then the stem of the name of the other element, and then it ends with IDE. Now, when you dissolve this compound in water, then the resulting solution will be an acid, and the name reflects that. In fact, the name of this compound here is hydrochloric acid when the hydrogen chloride dissolves in water, all right? So the compound by itself is hydrogen chloride before you add it to water, and then when you add it to water, the resulting solution is known as hydrochloric acid, all right? So that's just one example, and we're gonna see more closely how we name these acids like this one and others, all right? So to name binary acids, we identify the stem of the nonmetal name, all right? Just like we did before when it comes to other binary compounds. So for example, if the nonmetal is chlorine, then we use the stem chlor. If the nonmetal is iodine, then we use the stem name iodo or iod, and so on and so forth, right? One thing that they all have in common when you're naming these compounds is that the prefix hydro, let me go back to my pointer here. The prefix hydro is used in front of the stem of the nonmetal name, all right? So this is true for all binary acids. It's hydro, then the stem of the nonmetal name, and then that is followed with the suffix ic acid, right? So all binary acids start with hydro, the stem of the nonmetal name, and then ic acid, and that will give you the complete name of the binary acid. So the example I showed you before of hydrogen chloride by itself, before you add it to water, the name is hydrogen chloride. When added to water, then the resulting solution is called hydrochloric acid. Starts off with hydro, then the chlor, which is the stem of the name of the element, chlorine, and then the rest of the name of the acid would be ic acid, all right? So that's basically how we name the acids. Start off with hydro, the stem of the name of the other element, and then ic acid. Okay, here's another example, right? This compound, before you add it to water, is called hydrogen iodide, all right? Hydrogen iodide. So when you add this to water, it now becomes hydroiodic acid, hydroiodic acid. Again, hydro starts off with, then iod, then ic, and then acid. Okay, I think I have two more examples lined up. So this compound here, by itself, before you add it to water, is called hydrogen sulfide. And please note that even though there are two hydrogens here in the formula, we do not indicate that in the name. We do not use prefixes when it comes to these binary molecular compounds, which contain hydrogen and are acidic when you add it to water, right? So it's simply hydrogen sulfide, and that's a pure compound before you add it to water. After adding it to water, then the compound name or the resulting solution name is hydrosulfuric acid. Again, hydro we start off with, then the sulfur, which would be the stem, or actually the name of the actual element in this case, then ic acid, all right? So that's basically how we name these acids. So here's another example. So the name of this compound is hydrogen selenide. So can anybody tell me what the name of the corresponding acid would be? Anybody? Well, did somebody say? Let me see here. Hydroselenic acid, yes, and that's Karen Stepinski. That's correct. All right. So let me minimize this. So the name of the acid is hydroselenic acid, right? Following the same rule. Okay. Okay. So let's summarize what we talked about in terms of naming binary compounds. So there are three types of binary compounds we discussed. We talked about the binary molecular compound, which is formed between two nonmetals. Then we have the binary ionic compound, which is formed as a result of a combination with a metal and nonmetal. And then we talked about the special case of a binary compound where you have hydrogen bonded to a nonmetal, all right? So if you have two nonmetals, when you're naming it, one of the things that you have to take into account is that you have to indicate the number of atoms per molecule using prefixes, with certain exceptions, of course. If you recall, we said that if the first element has only one atom, then no prefixes are used. So that's as far as binary molecular compounds are concerned. In the case of binary ionic compounds, there are two types. You have one that is formed with metals of one type of cation, in which case you simply name it as starting off with the name of the metal and then the stem of the name of the nonmetal, and then ending with IDE, all right? Then over here, if we're talking about metal that can form more than one type of cation, then you have to determine the charge on the cation, right? And then you can use one of two methods. You can use the stock system, which uses Roman numerals, which indicate the charge on the cation, while the stem name of the nonmetal is added and then IDE, or you can use a classical way of naming these compounds where the ending of the name of the particular ion end with OUS and IC. So this one is more difficult because you don't use the direct name in most cases in this situation of the particular element. So instead of using tin, for example, let's say you're writing down, let's say you're dealing with the formula tin2, which is SN2. Well, that's the stock system I just mentioned using the Roman numerals. But if you were to use the classical system, then the name of the particular ion would be stannous, the stannous ion. So, you know, it's a bit more difficult when using the classical system in terms of relating the name to the ion charge and vice versa. So that's why the Roman numeral system or the stock system is more often used. Okay, and then over here, we just talked about the hydrogen nonmetal combination binary compounds. If the compound is not dissolved in water, then the name of the compound starts off with hydrogen, then the stem of the name of the nonmetal, and then ending with IDE. On the other hand, if you add that compound to water, then you're ending up with an acidic solution. And the way it is named is that you start off with hydro, then the stem of the name of the other element, which could be chlorine, bromine, whatever, and then it ends with ic, and then you simply add the word acid to complete the name of that compound. So this is just a summary of how we go about naming binary compounds. Okay, so we talked about binary acids. Now we're going to talk about another category of acids known as oxyacids. And as the name suggests, oxyacids contain oxygen. So the actual definition of an oxyacid is shown here. Oxyacids contain hydrogen, which all acids have, and oxygen, and one other element, all right? So that's basically what you'd find in any oxyacid, right? Now, the first thing we need to mention in terms of naming these acids is that the hydrogen is not expressed in the acid name, right? So unlike in the case of binary acids where you have to start off with hydro, in the case of oxyacids, you don't do that. You never start off the name of an oxyacid with hydro, all right? In fact, basically you're going to start off with the name of the other nonmetallic element, and I'm not talking about oxygen, but the other nonmetallic elements, such as in the case of sulfur. So the name of this acid, for example, is sulfuric acid. So you'll notice that there's no hydro in front of the sulfuric, it's simply sulfuric acid, and this is a formula, H2SO4, all right? So basically, the fact that it contains hydrogen implies it's an acid. It contains sulfur, which is indicated in this part of the name of the acid. And of course, it contains oxygen because it's an oxyacid, all right? Okay, so, and also the acid name here, or the acid part of the name, is what indicates the presence of hydrogen in the formula. Okay, so how do we determine the name of the acid? Well, one way of approaching this in terms of naming the acid is by looking at the name of the corresponding polyatomic ion, all right? And what you see on the screen here is basically how we determine the name of the acid, right? If the corresponding polyatomic ion ends with ITE, then the name of the corresponding acid will end with OUS acid. So you're going to replace the ITE with OUS acid. If the name of the corresponding polyatomic ion ends with ATE, then the name of the corresponding acid ends with ic acid, all right? So in that case, you replace the ATE with ic acid. And what is mentioned here is the relationship between these two. I don't remember if I mentioned this, or maybe I'm thinking of another class I'm teaching, but the difference between IT and 8 is basically that the ATE ion will have one more oxygen compared to the ion which has the name ending with ITE, all right? So in this case, the terms or the ending ATE or ITE does not actually indicate the number of oxygens, but basically you can see the relationship between the anion that ends with ITE and the corresponding anion that ends with ATE. And what you'll find always is that the anion ending with ATE will have one oxygen more than the anion that ends with ITE. Okay, so that's basically how we, those are the rules basically for naming acids. So let's see some examples of this. So the first example here is the sulfide ion, right? That's a formula for the sulfide ion. You can look that up in the tables that I've posted in Canvas, right? So the question now becomes, what would be the corresponding acid? So to get the corresponding acid, you simply add 2 hydrogen ions to this and you end up with this formula. And you'll notice a change in the name. The ITE ending of sulfite is replaced with OUS acid. So this is called sulfurous acid, all right? So you go from sulfite to sulfurous acid, all right? And that is basically how we name the acids. Replace the ITE ending with the OUS ending of the acid. Okay, here is another example. Now in this case here, we're dealing with an anion which ends with ATE, the sulfate ion. To get the formula for the corresponding acid, we simply add 2 hydrogens to the formula for the sulfate, and we end up with H2SO4, and the name of this acid would be sulfuric acid. So you see here, in terms of the name change, as you go from the anion to the acid, the ATE ending is replaced with ic acid, all right? So if the ending of the name of the anion ends with ITE, then the corresponding acid end name would be OUS acid. If the name of the anion ends with ATE, then the name of the corresponding acid ends with ic acid. Okay, some more examples. So in this case here, we have the nitrite ion, NO2 minus. So the name of the corresponding acid would be the nitrous acid, right? We replace the ITE ending with OUS, and the formula of the nitrous acid would simply be this with the hydrogen without the negative sign, and therefore that would be the formula. All right, and I think I have one more example, the nitrate ion. This is the formula for the nitrate ion. And if you look at the name of the corresponding acid, the ATE ending is replaced with ic acid, and therefore the formula for this acid is HNO3. So that's basically how we determine or derive the name of oxyacids based on the names of their corresponding anion. Okay. Any questions so far? Any questions? Any questions? Okay, so let's move along now to some other examples here. This chart here basically gives you some other examples of anions and their formulas and their names and the corresponding acid formula and their names, right? And it's the same thing that applies. So for example, this anion here is called a hypochlorite ion. So the name of the corresponding acid would be hypochlorous acid. This is called the chloride ion. So the name of the corresponding acid is chlorous acid. And then we have the chlorate ion. The name of the corresponding acid is chloric acid. And then finally here we have perchlorate ion. And the name of the corresponding acid will be perchloric acid. All right, so that's basically how that works. And this is just some other examples of oxyacids and their corresponding anions and their names. So I won't go through all this list here. I could just choose one or two. For example, this one here, this is called the phosphide ion. So therefore the name of the corresponding acid is phosphorus acid. And then over here we have the acetate ion, and the name of the corresponding acid is acetic acid, and so on and so forth, all right? Okay, so this is just a summary of what we just discussed in terms of the names of the acids based on, for oxyacids that is. So basically, when it comes to oxyacids, the formula begins with H, and the anion must contain oxygen. And then, of course, this is what we deal with when the name of the corresponding anion ends with "ite" or "ate." If it ends with "ite," then the anion name will end with OUS acid. I don't know if you can see it on your screen, but it's kind of cut off here on my screen. And then over here, if the anion name ends with ATE, then the name of the corresponding acid ends with ic acid. Okay, now there are other compounds that contain polyatomic ions. In fact, there's one, let me see here. Oh, so this is basically talking about naming ionic compounds which contains polyatomic ions. That is very simple. Just name the cation and then name the anion and put them together. But I'm thinking of one example of a compound that does not fit into the binary acid or polyatomic acid category. So let me open this up here to get into that. So there is a compound, a hydrogen-containing compound called, hold on, let me get rid of this here. Okay, so there's a hydrogen-containing compound called hydrogen cyanide. So let me write the name down first. Hydrogen cyanide. And this is a compound that if you're contemplating suicide, then you can inhale a lot of that to accomplish that purpose. The formula for this compound is, it's a gas, by the way. The formula is HCN, right? Gas. Now, as you can see from this formula here, it is not binary because it has 3 elements, right? Not 2. Remember, binary compound has only 2 elements. This has 3 elements, hydrogen, carbon, and nitrogen, right? At the same time, it's not an oxyacid because there are no oxygens, clearly, right? So this begs the question, how do we name the compound that, or the solution, I should say, that is formed when this is added to water? Because when this is added to water, it forms an acidic solution, HCN aqueous, all right? And the answer is, according to the powers that be in IUPAC, they said that you treat this as a binary compound for the purposes of naming this acid. So therefore, the name of this acid is hydrocyanic acid. Hydrocyanic acid. So this is a bit unique because it's not binary, it's not an oxyacid. So what IUPAC decided was that this would be treated like a binary acid where the name starts off with hydro, then you have the stem of the name of this combination here, the carbon and nitrogen, which is called the cyano group. So you have the cyan here, which indicate the presence of CNN, and then ic acid would be the rest of the name of this acid. So that's a kind of unique situation in terms of naming that particular acid. Okay, and I think that's the end of this chapter. All right, so we have successfully completed, we have successfully completed chapter 5. And now, unless there are any questions you want to ask concerning chapter 5, any questions? Okay, so we're going to move on to chapter 6. And chapter 6 is dealing, oh, by the way, before I move on to chapter 5, to chapter 6. So based on chapter 5, let me see. Oh, somebody has a question. Why do we add water or AQ? Oh, very good question. And I probably should have mentioned that. Okay, so Taryn Stepinski is asking, why do we add AQ to the end of the acid? Well, that just indicates that basically it's an aqueous solution, right? You're adding the hydrogen containing binary compound to water, right? And the resulting solution will be aqueous. So when it comes to binary acids, it's very important that you indicate, let me go back to this here. It's very important that you indicate that it's an acid solution by indicating AQ as a state symbol beside it. So for example, in the case of hydrogen chloride, that's a gas, right? So this is hydrogen chloride. Hydrogen chloride. But if you have HCl-AQ, aqueous, that's an aqueous solution, then that is called hydrochloric acid. So it's very important that you pay attention to the state symbols, hydrochloric acid. All right? Very important that you pay attention to the state symbols when it comes to binary hydrogen-containing compounds. If it's AQ, then you know it's an acid, and therefore you name it as such. But if it's a gas, then you can't name it as an acid. You have to name it as a binary hydrogen-containing compound. And in the case of HCl gas, that is hydrogen chloride. All right, so I hope that answers your question. Oh, and you're asking another question. Do we only do it on binary acids? And that's another very good question. And the answer is yes. Because in the case of oxyacids, it's not necessary to indicate AQ to show that it's an acid, right? So for example, H2SO4, without the AQ, it's already understood to be an acid, even though most often it's in an aqueous solution. But even without this, you know that this is an acid. That is not true in the case of binary acids. You have to indicate that it's in an aqueous solution by using the state symbol AQ to indicate that you're referring to an acid. Otherwise, we'd have to assume that you're not in an aqueous solution or it's not in an aqueous solution, and therefore you have to name it the other way. All right, so I hope I successfully answered both questions, Taryn. Okay, so as I said before, I'm finished with chapter 5. So let's move on now to chapter 6. And in chapter 6, we're dealing with chemical equations, which is something that's very important in chemistry in terms of representing what's happening in a chemical reaction. So basically, we use chemical equations, as stated here, to describe reactions in a shorthand fashion. All right, and the chemical equations by itself provides a means for us to, 1, summarize the reaction, and 2, display the substances that are involved in the reaction, and then 3, to show the products. All right, so that's basically what is imparted when you look at a chemical equation. It gives you the kind of information that we just stated. All right. Oh, and another important thing, which we'll talk about a whole lot in subsequent chapters, and that is that a properly written equation will indicate the relative amounts of everything that is involved, reactants and products, in a chemical reaction. All right. So we all know that in a chemical reaction, there's a change. You have atoms, molecules, and ions rearranging and combining in different ways to form different substances. So some terminology here that you need to be familiar with. The substances that are entering the reaction, these are called the reactants, right? So the reactants are basically the substances that react. And then the substances that are formed in the reaction, these are called the products, all right? And then, of course, as you go from reactants to products, you have a lot of things happening, mainly the breaking and the formation of bonds, right? That basically summarizes what happens in every chemical reaction. So as I said before, a chemical equation is a shorthand way of expressing a chemical change. And that's because the chemical equation uses chemical symbols and formulas for the reactants and products, and also some other terms which indicates things like the conditions of the reactions and the state of the different substances involved in the reactions and so on. So what you see here on the screen right now is an example of a chemical equation, right? And you see that basically there are 3 essential parts to a chemical equation. You have the reactants, which would be typically written on the left side of the equation. And on the right side of the equation, you have the products, and separating them is an arrow. The arrow basically indicates the direction from the reactants to the products, all right? So this is basically what you see in pretty much all chemical equations. The symbols that represents the different substances involved as reactants and as products, all right? Now, as you can see here, and you don't need to, what's the word I'm looking for? You don't need any detailed knowledge about the reaction to come to the conclusion that what's happening in this reaction is, in this particular reaction, is that the bonds are being broken between the iron and the oxygen. And we know that to be so because at the end of the reaction, over here, we have the iron by itself. So obviously there's a breaking of the breakup of the iron-free oxide to form the iron. And then also we can conclude that the aluminum is forming bonds with the oxygen to form aluminum oxide, all right? And that is what happens in every chemical reaction. You have the breaking and formation of new bonds to form different products. Okay, another important aspect, and this is very, very important. I can't overemphasize this enough. What is very important is that we use what are known as coefficients. And coefficients are basically integers or whole numbers that are placed in front of the formula of substances to balance the equation and to indicate the number of the different units, atoms, molecules, etc., of each substance that is involved in the reaction. So what you're going to see is that coefficients are very important. And the reason why they're very important is because they indicate, one, that atoms or elements are not created nor destroyed in a chemical reaction. And therefore, whatever the number of atoms that you started off with on one side of the equation for a particular element is the same on the other side. So going back to this example here, you'll notice, if you were observant enough, you'll notice that we don't have that situation where, for example, the atoms of aluminum would be equal to the atoms of aluminum on this side. So if you notice, we have an aluminum atom here, but we have a 2 here indicating that there are 2 aluminum atoms here, right? So we say that the equation is not balanced based on that. And the same is true when you look at the iron on this side and the iron on this side. We have 2 iron atoms represented here. We have only 1 here. So as far as the ions are concerned, they're not balanced either, all right? So what we do in order to balance the equation is that we place the appropriate coefficient in front of respective elements so that we end up with a balance in terms of the number of atoms of each element being the same on both sides. So by putting a 2 here in this example and putting a 2 here, we now have 2 aluminum atoms here, which balances with the 2 aluminum atoms here. And we have 2 iron atoms here, which balances with the 2 iron atoms here, all right? So now we can say that the equation is balanced, all right? So that's how we balance a chemical equation. We're going to talk more about that later on, but before we do that, some other things I need to get into with respect to the type of symbols that are used in writing chemical equations. In some cases, some information could be given about the conditions under which a reaction is taking place. So you might see something indicated like the temperature or the pressure of the system that is used in order to carry out the reaction. Or you might see something like this, right? So this small triangle here basically represents heat. So what this is telling you is that in order for this reaction to occur, you need to heat the reactants and you're going to end up with the products. So that small triangle here basically represents heat. So whenever you see that, you understand that for the reaction to occur, then some heating must take place, all right? You may see some symbols indicated right next to the particular substance, which basically tells whether or not the substance is in a solid, liquid, or gaseous state, or aqueous state. So if you see L in parentheses beside the substance, then you know that substance in this reaction is in a liquid state. As you can see here in this example, going back to this example here, you'll notice also that the aluminum has an S here, the iron 3 oxide has an S here, and the aluminum oxide has an S here. So basically, what this is indicating is that the aluminum, the iron 3 oxide, and the aluminum oxide are in the solid state, right? So that's just some additional information that is usually given in a chemical equation so that, whoever is reading it can interpret it correctly to have an understanding of the type of reaction conditions required in order for the reaction to take place. Okay, so I want to emphasize here again that because the equation is balanced, it satisfies the first law, the law of conservation of mass. That's what I want to say, the law of conservation of mass. If you recall, and this was a couple of chapters ago, we said that according to the law of conservation of mass, matter cannot be created nor destroyed, all right, in a chemical reaction. And the reason why that is so is because the atoms themselves are not created nor destroyed. In other words, whatever the number of atoms of a particular element that you start off with in a chemical reaction, you're going to end up with the same number of atoms of that element on the other side of the equation. And that is exactly what you see here in this balanced equation. You have 2 aluminum atoms here, 2 aluminum atoms. So the aluminums are balanced. No atom of aluminum is created nor destroyed. And the same is true for the iron. You have 2 iron atoms here, 2 iron atoms here, And also you have 3 oxygen atoms here, 3 oxygen atoms here, all right? So that's basically what is happening in every single chemical reaction. And later on, we're going to learn about how to go about balancing these equations. Okay, so some other symbols that are used in chemical equations. The plus sign basically are placed between the substances on either side of the equation. The arrow indicates the direction of the reaction, and it goes typically from the reactants to the products. S represents solid when placed right next to the formula for compound. L stands for liquid. Again, that is found next to the formula for compound. You have G for gas, and you have AQ for the substance that is dissolved in water. All right, so that's basically an aqueous solution we're talking about there. The triangle, we talked about this before, that represents heat, and that is typically written above or below the arrow. And in some cases, you might see the actual temperature or pressure recorded as well above or below the arrow. Now, this symbol here represents light energy. It's H nu. You learn the significance of that combination of English and Greek letters when you get to General Chemistry 1. So I won't get into that right now. But if you see that symbolism, it basically represents light energy. All right. There are some reactions that would take place when exposed to light. So, we call these reactions photopromoted or light-promoted reaction or photocatalyzed reaction. Okay, and this symbol here, I'll be honest with you, I haven't seen this symbol in a while. I remember seeing it more often when I was in high school, way back when, but I haven't seen this symbol in a while, but it actually stands for gas formation, right? So this is typically placed beside the symbol for a product that is a gas, all right? Okay, so how do we go about writing and balancing equation? Because this is a very important skill that you need to master before we can move on to other topics, all right? How do we go about writing a balanced equation? Well, firstly, to balance an equation, we have to make some adjustments to the number of atoms of each element so that they're the same on both sides, right? As we said before, we have to indicate that the atoms are not created nor destroyed as you go from the reactants to products, all right? So one thing we need to do, or I should say we should never do in our effort to balance an equation, is that we change the formula of the compound. So we don't modify the formula for the compound to balance an equation, all right? In fact, what we have to do is make changes to the coefficients in order to achieve the balance of atoms on either side of the equation. So what I'm going to go through now are the different steps for balancing chemical equations, right? Let me move this out of the way here. Okay, so the first step is that we identify the reaction. And you may or may not want to do this, but if you're learning this for the first time, well, you might find this helpful. It says here that you need to write a description or word equation for the reaction, all right? So this is an example of a word equation or description of a reaction. Mercury 2 oxide decomposes to form mercury and oxygen, all right? So that's the first step. And in some cases, actually, you might be given this in a question. So, you don't need to actually do this step. But that would be the step, the first step. If you're not given this statement, you might be given something else, some information based on which you can write down the statement. So that's the first step. So this is basically the same thing. The only difference is that we're writing it in an equation form, but we're not using symbols. We're using the actual names of the different substances involved as reactants and products, all right? Then we write an unbalanced equation for the reaction. So in this case, we have to make sure that the formulas are correct for both the reactants and the products. The reactants are written on the left side of the arrow, and the products will be placed on the right side of the arrow. So in the case of the reaction we talked about, this would be the formula for mercury 2 oxide that is placed on the left. And then on the right side, we have mercury and we have oxygen. And let me remind you again that oxygen is one of those elements that exist as a diatomic molecule, right? So therefore, if you're writing an equation involving oxygen, then it would be written as O2, All right, so that's something you need to be aware of. Remember, there are 7 elements that exist as diatomic molecules. There are fluorine, iodine, bromine, chlorine. Then you have oxygen, hydrogen, and nitrogen, right? You need to remember those elements as elements that exist in nature as diatomic molecules. So in this case, it's oxygen. So the formula is O2. Now, you'll notice that this equation here is not balanced, because if you look at it carefully, you'll see that while the mercury atoms are balanced, you have 1 on each side, but the oxygens are out of balance, because in this case here on the left, you have 1 oxygen atom. On the right, you have 2 oxygen atoms. So therefore, we need to take another step, all right? And as stated here, we cannot change the formula. So we won't be making any adjustments to the formulas of these compounds. So for example, we won't remove the 2 here to balance the oxygens, because O2 exists as O2 in nature. Okay, so the next step is that you count and compare the number of atoms of each element on both sides. And we actually did that already. As we said before, we have 2 oxygens here on the right side, 1 oxygen on the left side. So they're out of balance, and therefore the question is, how do we balance the oxygens? And we do so, let me just skip all this here. Well, okay, before I move on to that. So this is us basically showing you that the mercury is balanced. You have 1 mercury atom on the left, 1 mercury atom on the right, so the mercury atoms are balanced, all right? But as I said before, the oxygens are not balanced, because on the left side, you have 1 oxygen atom, and on the right side, you have 2 oxygen atoms. So what do we do? Well, what we do is that we need to multiply something by a coefficient. A coefficient would be an integer, all right? And we place the coefficient before the formula such that it multiplies every atom in the formula by that coefficient. So in the case of this equation, because you have a 2 here and 1 oxygen here, then what we need to do is multiply or place a 2 in front of the mercury 2 oxide, so that you're going to end up with 2 oxygen atoms on the left, like that. So now we have the oxygens that are balanced as a result, all right? However, we're not finished yet, because even though the oxygens are balanced now, by placing this 2 here, that multiplies the mercury atoms here by 2. And now, as a result of that, the mercury atoms are not balanced, because you now have 2 mercury atoms on the left side and 1 on the right side, all right? So let me skip all this here. The mercury atoms are not balanced. So this begs the question, what do we do? How do we get the mercury atoms being equal on both sides of the equation? And the answer is, let me just skip this here. The answer is you simply place a 2 in front of the mercury on the right side. And now we end up with a balance of the mercury atoms, right? We have 2 mercury atoms on the left, and that balances with the 2 mercury atoms on the right. So now the mercury atoms are balanced, the oxygen atoms are balanced, and therefore the equation is balanced, right? As seen here, all the atoms are balanced. So therefore now we end up with a balanced equation, and that would be the final answer, all right? Okay, so are there any questions about this particular example? Any questions? Any questions? Okay, so let's move on to this example. So in this case, they gave you the equation of the reaction where they give you the actual names of the products and the reactants, all right? So the first step in this process is that we have to figure out what the formulas for these compounds are, all right? So based on the rules that we learned earlier, we know that the formula for sulfuric acid is, hold on, let me turn on my pen function here. Okay, so the formula for sulfuric acid is H2SO4. And the, excuse me, ooh, sorry about that. The formula for the sodium hydroxide is NaOH. So that takes care of the reactants. And then on the product side, based on the rules that we learned earlier, The formula for sodium sulfate would be Na2SO4, and everybody knows the formula for water, which is H2O. So basically what we have done here is written down the unbalanced equation. So now we have the task of balancing this equation, and that means that we have to do an atom count of each element on both sides, starting with the hydrogen here. We have 2 hydrogens here, and on the right side, we have 2 hydrogens here. So the hydrogens are balanced so far. Let's look at the sulfurs. We have 1 sulfur atom here and 1 sulfur atom here. So that is balanced so far. But now we get to the oxygens. Let's see the oxygens. We have 4 oxygen atoms on this side, and we have 1 oxygen atom on that side. So that's 5 total. And then on the right side, we have 4 oxygens here. We have 1 here, 5. So the oxygens are balanced. Okay, so far so good. Let's look at the sodiums. Here we have 1 sodium atom, but guess what? We have 2 sodium atoms here. So how do we balance the sodiums? Well, we put a 2 here, all right? We put a 2 here, and that balances the sodium. Now, because we put a 2 here, that affects not only the sodium atom, but it affects the oxygen here as well, right? So that means that the number of oxygen atoms are not balanced, because now we have 6 oxygen atoms on the left, and we have 5 on the right. So this begs the question, how do we balance the oxygens? Well, what I would do is put a 2 here in front of the H2O. So we're going to end up now with, on the right side, 4 plus 2 oxygens, right? 6. So the oxygens are balanced. And then let's look at the hydrogens. We have a total of, hold on 1 minute. We have a total of, why is this thing active? Okay, we have a total of 2 plus 2, 4 hydrogens on the left side. And here we have 2 times 2, 4 hydrogens on the right side. So now the equation is balanced. All right. So that's just another example of how we go about balancing chemical equations. All right. And this is a very important skill that you need to master, because as you're going to see in future topics that we're going to encounter, very often a question might be asked which involves some calculation. And in order for you to answer the question correctly, you need to start off with a balanced equation. Now, in some cases, you may be given the balanced equation, based on the question that's given. In other cases, you may be given an unbalanced equation, which means that you have to balance it. And yet in other cases, you may be given a word description of the reaction, and therefore, based on that, you'd have to figure out what the equation will be. And after that, you'd have to balance it. All right. So it all depends on the type of question that you may be facing at a given instant. Okay. Any questions about this example? Any questions? Okay. Here's another example. Now, in this case, I would not expect you to know the formula for butane, right? So let me write the formula for butane here. Excuse me. The formula for butane is C4H10, all right? That is reacting with oxygen. Remember, we said that oxygen is a diatomic molecule, so we're going to put O2, and then it says it forms carbon dioxide, which is CO2, plus water. And everybody knows the formula for water is H2O. All right, so the task is to balance this equation. So I'm going to turn it over to you guys. So how would you go about balancing this equation? What would be the first thing that you would do? Anybody?
So I would maybe make a chart. I'd have C, H, and O for carbon, hydrogen, and oxygen. And
I'm sorry, repeat that.
I would maybe make a chart of the
Okay.
carbon, hydrogen, and oxygen and calculate how much is on each side first.
Okay, so, let's start off with the carbon. On the left side, how many carbons do we have? I'm sorry.
4.
Okay, and how many carbons do we have on the right side?
1.
1, okay? So how would you balance the carbons?
You'd have to put 4 next to the carbon dioxide.
Okay, so you put a 4 in front of the carbon dioxide. Very good. Okay, let's look at the hydrogens. How many hydrogens do we have on the left side?
10.
And how many do we have on the right side?
2.
Okay, so how would you balance the hydrogens in this case?
Make the coefficient of water 5.
Okay, so we're going to put a 5 as a coefficient for H2O. Very good. Then we have the oxygens, right? How many oxygens do we have total on the left side?
2.
2. And how many do we have on the right side total?
3.
Huh?
9. Sorry.
You sure? Count it again.
4, 8 plus 1, 9.
Mm,
Unless I'm doing it
Nope.
wrong.
Anybody want to help her out? Okay, let's see what's in the chat.
Oh, I see.
13. That's correct, Taryn. You have a total of 13 oxygens. Whoops. 13 oxygens on the right. Okay, so here we have a situation where we have 2 oxygens on the left and a total of 13 oxygens on the right. So how would you balance this particular situation with the oxygens? You have 2 oxygens on the left and a total of 13 oxygens on the right. Anybody?
Would you be able to write, like, I know that you can't have like 13/2 atoms of oxygen, but if you do that and then multiply the entire equation by 2, would that work?
You read my mind, my dear. That's exactly what I would have done. So who said that, by the way? I didn't catch. I want to give credit to the person who said it. Who was that?
Taryn.
Taryn. Okay, yes. So yes, I would put 13/2 here. And to explain the reason why that is so is because 13/2 times 2 gives you 13 oxygen, right? Which balances with the 13 oxygens total that you have on the right side. But as Taryn correctly said, you cannot leave this as a fraction because remember the coefficients must be expressed as integers. So in order to do that, what I would do is multiply this entire equation here. Whoops, okay, what's going on here? I would multiply this entire equation here by 2. So when you do that, you're going to end up with 2C4H10 plus 13O2 to give 8CO2 plus 10 H2O. And that's basically how you do that. All right. And I recommend students, especially those who are learning this for the first time, just to do one final check through to make sure everything is balanced. So if you do that, you'll notice that you have 8 carbons on both sides. You have 20 hydrogens on both sides. You have a total of 26 oxygens on both sides. 8 times 2, 16 plus 10, 26. So now the equation is balanced. All right. Okay, are there any questions about this particular example? Any questions? Any questions? Okay, you know what? Let's do a couple more examples just to make sure that we all are on the same page. So I'm just going to write down an unbalanced equation here. Okay, what am I going to write? Okay, I'm going to start with this one. This one is relatively simple. Okay, so that's the unbalanced equation. So let's hear it. How would you go about balancing this equation? Anybody? Well,
Okay. So I just use the same process. And for the
Mhm.
sake of guess, I would
I'm
just
so-
put,
I'm sorry, go ahead.
so the equation is going to need a coefficient of 3 next to the hydrogen atom
Mhm.
and a coefficient of 2 next to NH3. And it will
Mhm.
have 6 hydrogens and 2 nitrogens on each side.
Okay. Okay, that's correct. That's correct. Okay, any questions about this? I don't think I need to say anything more. Anybody has any question about this example? Okay, let me come up with another one. Suppose you're given this. Suppose you're given, okay, let's see if you guys can do this one. HNO3 to form NO2 plus H2O plus O2. Okay, so any ideas? Well, oh, somebody's saying something in the chat. Wow. Taryn, I'm not sure if that is correct. You're saying that there should be 2, 1, 2, 5. I'm assuming
Sorry,
that's
not 2 on the first one, 4 on the first one.
okay. So you're saying, hold on 1 minute. So you're saying that there should be 4 and the NO2 should have a 1. Well, I can't see that is incorrect already.
Yeah, no, I'm wrong. I forgot about the oxygen and water.
Right. So yeah, I wouldn't, let me move this aside here. Let me erase, oops. Let me erase this here. Erase this here. Okay, anybody else? Okay, let's start with the hydrogens. How many hydrogens do we have on the left side? Well,
1.
1, right? And how many do we have on the right side?
2.
Okay, so how would you propose we balance the hydrogens?
A coefficient of 2. It just takes a while because there's a lot.
Yeah, no, a coefficient of 2 in front of the HNO3. Very good. Okay. What about the nitrogens? We have, because of this 2 here that we just placed here, we now have 2 nitrogens on the left. We have 1 on the right, so I would put a 2 here, right? So now we get to the oxygens. How many oxygens do we have total here on the left side?
6.
6 oxygen, 2 times 3, 6 oxygens, right? And how many total do we have on the right side? We have 2 times 2, 4, plus 1, 5, plus 2, 7. So we have 7 oxygens on the right side. So how would you propose we balance the oxygens? Well, we have 6 oxygens on the left, and we have 7 oxygens on the right. So how would you balance the oxygens? Okay, let me give you a little help. What I would do is that I would put a half right here. All right? And the reason why is because if I put a half right here, a half times 2 gives you 1 oxygen, plus 1, that's 2 oxygen, plus 2 times 2, 4, that's 6 oxygen. So now the oxygens are balanced. So you're going to end up with 6 oxygen on both sides. But again, remember, we cannot leave this as a fraction. So what I would do is, like I did in another example, and multiply that by 2, the entire equation. So therefore, the final answer becomes 4HNO3 to give 4NO2 plus 2H2O plus O2. And now the equation is balanced because now you have 4 hydrogens on both sides, you have 4 nitrogens on both sides, and you have a total of 4 times 3, 12 oxygens here. 4 2s 8 plus 2, whoops, 4 2s 8 plus 2, 10 plus 2, 12. So now the entire equation is balanced. So as you can see, balancing an equation or balancing equations is something that you have to practice in order to become good at it, right? And I would strongly recommend that you go to your textbook, or you can go online even and find some problems and practice this particular skill, right? Just find, any unbalanced equation that you can come across and then try to balance it on your own, all right? Okay, any questions about this example? Any questions? Okay, so let me go back to the slides. Okay, we're almost through. So let's talk about the type of chemical information that you can get from a balanced equation. Now, this thing is not, what's going on here? You know what, let me go back to my pointer. Okay, so some information can be obtained from a chemical equation. So for example, if you have this formula of water, H2O, of course, that tells you about the composition. 2 hydrogen atoms and 1 oxygen atom per molecule. Or it can just represent a molecule of water, right? But in an equation, formulas represent units of individual chemical entities or moles. So for example, if you look at this equation right here, the reaction between hydrogen and chlorine to form hydrogen chloride. There are a couple of ways that we can interpret this. One way is that 1 molecule of hydrogen will react with 1 molecule of chlorine to form 2 molecules of HCl. So you see, this underscores the importance of having a balanced equation, because based on the coefficients in the balanced equation, we can see and determine the relationship between the different entities involved in the reaction. There's a 1-to-1 to 2 molecular ratio between the hydrogen, the chlorine, and the hydrogen chloride, all right? But as stated here, it can also represent, in terms of the formulas, it can also represent the moles of the substances involved. So to illustrate that, let's look at this equation right here. We have this molecule, which is propane, the formula is C3H8, reacting with oxygen to form carbon dioxide and water. And the equation is balanced as it is right here, all right? So one can see that in terms of the molecular relationship between the different substances in the equation, they basically parallel the coefficients for the balanced equation. 1 molecule of propane will react with 5 molecules of oxygen to form 3 molecules of carbon dioxide and 4 molecules of water, right? Now, what is true at the molecular level, we can establish a similar relationship at the molar level. So in other words, 1 mole of propane will react with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water, all right? So the coefficients in the balanced equation can be used not only to establish the molecular ratio between the different substances involved as reactants and products, but also can establish the mole ratios between the substances involved as reactants and products, all right? And again, this underscores the importance of having a balanced equation, because the balanced equation is what tells you the relative relationship between the different substances involved in the reaction, either at the microscopic level in terms of the molecules or at the molar level in terms of the moles of the different substances involved. One other thing I want to point out here, and this goes back to something we talked about, the number of atoms of each element present on both sides are the same, right? So for example, you see that there are 3 atoms of carbon on both sides. You have 8 atoms of hydrogen on both sides, and you have 10 atoms of oxygen on both sides. You have 10 here, and you have 6 plus 4 on the right side. So this again underscores Dalton's atomic theory that in a chemical reaction, atoms are not created nor destroyed, but basically you have rearrangement, bond breaking, and bond formation occurring. Another thing I want to point out is that because of the fact that no atoms are created or destroyed as the reactants are converted to products, that means that the mass, total mass, is conserved in a chemical reaction. So in other words, if you add up the total masses on a per molar basis of the reactants and do the same for the products, you're going to find them to be the same, all right? So those are just a few conclusions we can come to when it comes to not only writing down a balanced equation, but what the equation tells you in terms of the relative amounts of the different substances involved as reactants and products. All right, and believe it or not, that's the end of chapter 6. So what does that mean? That means that as far as assignment goes, let me go to files, and then let me go to assignments. You should be able to do the assignments. Well, wait a minute. Let me make sure that all these assignments are. Okay, so based on what we have accomplished today, you should be able to do assignments 12. Let me publish this. And 13 from chapter 5. And then in the case of chapter 6, there's only one assignment in chapter 6. And that is this one right here, which is published here, but I need to publish that folder. So as far as chapter 6 is concerned, there's one assignment, all right? So I'm going to open up the Canvas portal for you to be able to submit those assignments, and they will be due by Monday of next week, all right? So remember, oh, by the way, before I forget, because I've been having some issues with grading some of your work, please make sure that you submit your handwritten work. I don't want anything typed, all right? I know a couple of you have typed up your work, which I understand the need for, but please don't do that, because based on what I've been grading so far, for some of you guys, when you type it, you do some incorrect things. Like, for example, when you're writing down the formulas or typing the formulas for substances, you don't indicate the numbers of the atoms as subscripts, for example. That's just one thing that I've observed while grading some of your work, all right? There was another issue which I can't recall right now, but if I remember, I'm going to post it in the announcements for you guys to see, All right. Okay. So that's basically it, unless there are any questions you guys have. Any questions in the remaining 4 minutes that we have left? Any questions? Okay, so if there are no questions, then that's pretty much it for today. So I'll see you guys next Monday. All right, at 4 o'clock. Okay, so until then, you have a good day and a good weekend, and take care.